Okay, in an effort to help y'all not miss the easy ones while, getting the hard ones on the test, I figured I would do one last video that went back to the really easy ones that usually introduce the section in all the textbooks. We didn't do those at the beginning because I wanted to enter in by means of the inscribed rectangle inside the triangle, because it's something that you had seen before and it seemed a rather appropriate way to do this. But if you're given something like, okay, two numbers, product is 185, and I want you to minimize the sum. Okay? Now, obviously, that's really, really straightforward. That has nothing to do with geometry or anything like that. Well, not directly. And therefore, we basically are just going to be dealing with numbers and the representations of those numbers by variables. So I know that the product is x times y. We'll just use x and y since we're familiar with that. And the sum is x plus y. Okay? Now, I want to minimize the sum while dealing with this. Well, this is going to help me by getting me y in terms of x. So now, I don't have x plus y, I have x plus 185 over x. So it's in terms of a single variable now. And when I take the derivative, I get 1 minus 185x to the negative 2, or 1 minus 185 over x squared. When I get a common denominator, that's going to be that. And of course, if I'm looking for critical values, and this is my first derivative, I need to look for where the derivative is either a, 0, or b, undefined. Well, let's talk about undefined first. Undefined is only going to be where x is equal to 0. Well, that doesn't really make any sense, because if x is 0, the product is not 185. On top of the fact that 0 is not in the original domain because it's in the denominator here, okay? So that critical value is kind of a false one, okay? What I do, however, have is I do have root 185, okay? And let's pretend that we're just dealing with positive numbers here, okay? Two positive numbers which give us this scenario. So root 185, and therefore the sum, when it's minimized, is going to be 2 times 185, right? Because if x is root 185, then y has to be root 185 in order to get me 185. Okay? And this should not surprise us, because for a second there I said this has nothing to do with geometry. Well, the way that the question is asked does not directly say geometry. But this is really just a question about, give me a rectangle of a particular area. How do I minimize the perimeter? And I minimize the perimeter when it's a square, right? When x times y is 185, x and y being the square root of 185, that is a rectangle of given area where the perimeter, which of course would be twice this sum right here, is minimized. So it actually does have something to do with geometry, just not directly, okay? Now, let's say we're looking again for two positive numbers, and let's say that one number is the reciprocal of the other, okay? And you're looking to minimize the sum. One number is the reciprocal of the other, okay? Now I need you to minimize the sum. Well, this is actually set up in much the same way. So I know that the sum is going to be x plus its reciprocal, or x plus x to the negative 1. Okay? Well, that gives me a derivative of 1 minus 1 over x squared, or x squared minus 1 over x squared. How do I minimize the sum? Well, I minimize the sum by choosing the number that has itself as its reciprocal. x is equal to 1. Because that's the only positive critical value here, is because that numerator factors, of course, into x plus 1 and x minus 1. Okay? X is equal to 1. 1 plus 1 is 2. Right? But 2 plus 1/2 is 2.5. 3 plus 1/3 is 3 1/3. Okay? And that kind of makes sense that this will be the smallest one. Okay? So let's go ahead and let's look at maybe 2 more examples. Now, this probably won't be a very long video. Let's go ahead, and sometimes they ask us something like, okay, y is equal to x squared is obviously a parabola. Let's say I'm given the point 2 1/2. I want to know the point on this graph that is closest to that point. Okay? So here's the thing. What I really am trying to minimize here is the distance formula. Okay? Because if I see this, okay, let's go ahead and draw it real quick. Can't hurt. 3, 4, 1, 2, and we see the fact that, the graph looks something like that, and my point is here. Okay? Well, whatever the distance is, okay, it's going to make a right triangle. Because remember, the distance formula is just Pythagorean theorem in disguise. So if you recognize that, to maximize the distance formula is to maximize the radicand underneath that radical. So actually, if we take the distance formula, knowing that we're finding the distance between 2 1/2 and x squared, right? Because if you say y is equal to x squared, you're saying that for every ordered pair, x, y, your y can be substituted in with x squared. Okay, so if I want to find the distance formula, I know that it's going to be x squared minus 1/2 squared plus x minus 2 squared. But like I said, if you maximize the radicand, you maximize the radical. So you could actually get rid of that. You could actually, deal with it as, or let's just call it, d sub 2. And this winds up being x to the 4th minus x squared plus 1/4 plus x squared minus 4x plus 4, or x to the 4th, that and that conveniently cancel out, minus 4x plus 4 1/4. Okay, so 17/4. So let's go ahead and take the derivative of d prime of x, and we get 4x cubed minus 4. And basically, if we set that equal to 0, sorry about that, we know that it's going to be x cubed minus 1 is equal to 0, because you can quickly divide through by the 4. So x is equal to 1 is the value that minimizes that. Okay? What that tells me is this. Okay? Because the straightest, do I want to get into that? Nah, I really don't. Okay, but basically all we've done here is that instead of maximizing or instead of minimizing the distance formula, I minimize just the radical underneath. Because the moment that I maximize or minimize the radical, I'm maximizing or minimizing the whole thing. I basically multiplied it out, combined terms, took the derivative, set it equal to 0, found the critical value, and that critical value, it makes sense that it has to be the minimum. I mean, you can actually do a second derivative if you want. I mean, second derivative of x is equal to 12x squared, and of course, if you're going to plug in 1 into here, it's going to be concave up. Concave up implies a minimum, okay? But x is equal to 1 is your minimum value, which means 1, 1 right there is the point that is closest to 2 1/2 on that particular curve. And you can do it for any function. Let's go and do one more. Let's say that I am given f of x is equal to root x minus 8, and I want to find the point on there that is closest to 12, 0. Okay, well, I know that that is going to be x root x minus 8, okay? And therefore, I know that the distance is going to be the square root, but I'm going to go ahead and dispense with the square root. X minus 12 squared plus root x minus 8 squared. So that winds up being x squared minus 24x plus 144 plus x minus 8, or x squared minus 23x plus 136. Well, if that's the case, then d prime of x is 2x minus 23, or x is equal to 23 halves. And of course that's, 11.5. So 11.5, or 23 halves, comma, if I plug in to here, that winds up being root 3.5, or, root 7 halves. That is the ordered pair on that curve, which is closest to 12, 0. Okay? So all you have to do is you just take the function, turn it into its implied ordered pair, the general ordered pair, which this tells you of, and then basically do the distance formula. You can get rid of the big radical because basically, like I said, if you minimize the radicand, you'll be minimizing the radical. And then you just do the distance formula in terms of that variable of x, take the derivative, find the critical value, and find the ordered pair that it implies. Okay? Well, I hope that that is easy. Be on the lookout for some videos on antiderivatives.